Hi, this is Ms. Fitzmaurice. This video is an introduction to torque. So in this video, I'm going to explain what torque is, how to calculate torque from a single source or a single force, and how to calculate the net torque on an object. So before I formally define torque, I want you to think about this situation. There is a door that you want to open. Okay, so here's the door, and let's say that the hinges to the door are over here. And what I want you to do is I want you to actually try this, and I want you to try pushing in two different places. So, find a door that pushes, that doesn't pull, and I want you to try pushing right here, really close to the knob, and then I want you to try pushing right here, really close to the hinges, but not quite at the hinges. Okay, so actually pause the video and go try this. Hopefully you're near some type of door. And let's call these places place A and place B. And hopefully what you notice is that it's a lot harder to push the door open when you're pushing at A. Okay, or we could say you need more force. Okay, force applied for the same effect. Alright, so another example that's helpful to think about this, and this is supposed to be a hammer and a nail. If you are trying to nail something into a surface, you get a lot more for the force that you apply if you hold the hammer close to the end of the handle than if you hold it really close. So you get more effect if you hold here and less effect if you hold right here. Okay, so these two things are both an example of how the same force can get you a different effect depending on where you apply the force. So far we've just talked about the size of a force and how it creates acceleration. What we're going to be talking about in this coming unit is about how the place you apply a force determines not the amount of acceleration, but the amount of angular acceleration. Okay, and this brings us to the concept of torque. So torque is kind of like the rotational equivalent of force. Okay, and basically it depends both on the size of the force and where you apply it. So this tau, this is our torque. And the units for torque are newtons times meters. Torque is equal to the force you apply times the distance from the pivot. Okay, and more importantly, it's the perpendicular force that you apply times r, the distance from your pivot. So I'm going to just put perpendicular force, and I'll explain that a little bit more in a minute. Perpendicular force, and then distance to the pivot point. Okay, to show you what I mean by this force perpendicular, let's go back to the example of the door. Okay, so instead of drawing you a side view, I'm drawing a top-down view where this is the door, and we're looking kind of down at where the door would be. Here's the hinge in orange. And, you know, say your door's at a certain position. If you apply a force, so some kind of force applied at the handle, but towards where the door is pivoting, where it's turning around, then it's not going to pivot. Okay, but if you took the same force and you apply it at a 90-degree angle, okay, and it's at a 90-degree angle to the direction between the contact point and where you're applying the force. So hopefully you guys can see these two things are parallel, okay, and then these two are at 90 degrees, then this force, which is at 90 degrees, it is perpendicular, it will pivot the door. Okay, now the question comes, what if the force is not exactly at 90 degrees and not exactly at 0 degrees? What if I kind of apply the force at an angle? So let's say I'm applying this force at the same point, but I'm applying it in this direction right here. Should automatically start thinking, okay, well, I'm going to break this force up into x and y, and the part of the force that I care about is only the perpendicular part. So here, FAX or FAY would be what I put into F perpendicular. So it's only the part of the force that is perpendicular. And I'm just going to abbreviate that. Now the R is the distance between the pivot point where this thing is rotating or swinging and the place where you've applied your force. So in this case, if you're putting your force at the edge of the door, that would just be the distance between the hinge and the place where you're applying the force. And I'm going to give you one alternate version of this formula, and that's that torque is equal to F, so the total force, times R, the distance between the force and the pivot point, and times sine of theta, okay, as long as you define this angle as the angle between the R and the force. Okay, so I'm going to draw you an example of that again with our door. Okay, so here, if I applied a force at the edge right here, my R would be this distance right here. Okay, so I have applied some FA, and the angle that I'm going to plug into sine theta will be the whole angle between here and here. So you can use this other alternate version as long as you're able to remember the definition of this angle. It's the angle between the radius and the force. Okay, so here's an example calculation. What if I have a meter stick, and the meter stick is put so that it's kind of positioned, it's not quite balanced, and so you can probably guess it's going to tip this way. And I want to know what is the net torque on my meter stick. Okay, so you can probably imagine, and let's say, just so we can have a number that, or a variable, the mass, let's call the mass m. Okay, we know that we have a couple forces acting on our meter stick. So if I was to draw a force body diagram, I have Fn from this pivot thing. Okay, I have Fn coming up right here, and then I have Fg, but we can think of, it's coming from everywhere, but it balances out to come from the middle of the meter stick, Fg. So I have Fn, and I have Fg. Now, if I want the torque on the meter stick, I have to specify what's called a pivot point. And, in this case, this is a really practical pivot point to pick because that's where there's an actual fulcrum. Okay, so if I want the total torque on the meter stick, then I'm essentially adding up all the different torques, and that's going to be the torque from Fn plus the torque from Fg. Okay, and so that is going to be Fn times the radius of Fn, so the distance from this pivot point, which happens to be 0 because it's right on the pivot point, times sine theta. Okay, so since the radius is 0, it's right on the pivot point, that term goes away, plus mg, because that's our force, our Fg, times r, and then sine theta. So it looks like this is acting at a 90-degree angle. So here's our r. Okay, and you can probably figure out if we have the pivot at 40, then r has to be 10 centimeters or 0.1 meters. So we have, and then we have a 90-degree angle here, so we have mgr sine theta. Sine of 90 is 1, so we have just plus mg times 0.1. Okay, and our torque will just be mg times 0.1, or mg over 10 newtons times meters. Alright, the last piece of information you need about torque right now is the direction of torque. Okay, so you can imagine that we want some mathematical way of explaining whether you are pushing a door, you're pushing right here, so the door would spin this way, okay, and we could call that, if we wanted, counterclockwise. Okay, versus if you push the door the other way, and the door spins the other way, which we call clockwise. Okay, so the way that we talk about that mathematically is we make one positive and one negative. Okay, and the way you can remember it, so you could remember that counterclockwise is always a positive number and clockwise is always a negative number. Or you can use what's called the right hand rule. Okay, and so the right hand rule is just this. You take your right hand and curl your fingers in the direction of your rotation the way your thumbsticks tells you the direction of the torque. Okay, and this is basically a way to keep track of if you had, 7 different forces, and some of them made your door rotate clockwise and some made it rotate counterclockwise. When you were finding the net torque, you would want some to be positive and some to be negative so that you could find out the total effect. Alright, so tomorrow in class we're going to be calculating net torque on systems and also doing this thing called rotational equilibrium, where we figure out the sizes of forces that are applied in order to keep something from rotating.